Hello, good afternoon. I'm Jeehoon Kim, and I just earned my PhD from Yonsei University. Oh, thank you. It is a great pleasure to share our research with you. So the title of today's presentation is Automated Defect Inspection in Building Construction with Multi-Sensor Vision and Deep Learning, and they are my co-authors. Yeah, as you may know, there are several issues such as substandard finishing work, insufficient workproofing, or structural flaws during building construction. And these kinds of defects can lead to serious issues such as compromise of safety, increase in cost, and construction delay. Among these defects, structural flaws are really critical issues because they impact the building's long-term durability and its aesthetic integrity. So in this study, we are focusing on monitoring structural defects such as distortion in frameworks and sagging of floors and ceilings. So there will be many methods for monitoring structural defects, such as vision-based method and TLS-based method. However, vision-based method is not suitable for monitoring structural defects because it only acquires two-dimensional data. And the TLS-based method is also not appropriate when you're considering the cost or the time for data acquisition. So a cost-effective and accurate method for monitoring these kinds of structural defects in building construction is needed. So here is the research framework we propose. So as you can see, the framework is composed of 3 steps. The first step is point cloud data acquisition through multi-sensor vision. And the second step is point cloud registration for visualization purpose. And the last step is defect inspection from point clouds. So this research has been submitted to JCCA and currently under review. So let me start with data acquisition first. As you can see in this figure, we developed a backpack platform for data acquisition in this paper. So as you can see, 4 RGBD sensors were attached on the platform, and we calibrated these RGBD sensors by utilizing this TLS data as the ground truth. So in this process, these RGBD data were registered based on TLS data using a deep learning based registration algorithm, which is called DGR. So yeah, and in this figure, you can see that you can see the effectiveness of the proposed calibration method compared to the traditional calibration method. So discrepancies between point clouds has resolved by applying the proposed calibration method here. And the next step is point cloud registration for visualization. So as you can see, all the acquired point clouds were merged and registered using DGR to generate a comprehensive and precise point cloud map. And in this process, misalignment between point clouds has been resolved through error propagation between point clouds. And the next step is defect inspection. So here, from the raw point cloud data, we detected 2 types of defects. And the first was framework distortion, and the second was sagging in ceilings and floors. So in the raw point cloud data, we segmented multiple planes and then extracted only vertical walls and calculated angles from it. So we finally visualized all the calculated angle on the point cloud map. In the case of ceiling to floor distance analysis, after plane segmentation, we extracted only ceiling and floor points and calculated the shortest distance and visualized the abnormal distances on the point cloud map. So to verify the proposed method, we acquired point cloud data from 2 apartment units, and we also obtained 3 data sets for each apartment unit. We additionally acquired TLS data along with RGBD data to evaluate the accuracy of the proposed method. So here is the experimental result. As you can see, we successfully obtained a comprehensive point cloud map, which can be used for defect visualization. So as you can see, in this process, misalignment between point clouds has been resolved successfully through error propagation. And yeah, in the angle measurement result, here are the calculated angles from TLS data, while these are the angles from RGBD data. So you can see that the difference between the calculated angles from TLS and those from RGBD data were really small, showing an average error of 0.3 degrees. So here you can see that the calculated angles were visualized, yeah, on the point cloud map in the appropriate locations. So in the ceiling to floor distance analysis on areas with abnormal distances were well visualized. So here's the conclusion of the study. So this study proposed a novel pipeline for monitoring structural defects during building construction using multiple RGBD sensors. And also we created a comprehensive 3D point cloud map, and we visualize all the detected defect information on the point cloud map. So in conclusion, this approach not only significantly reduced the time required for data acquisition, but also maintained a high level of accuracy. So here are some future studies. I think there is a need to set some benchmarks for data acquisition or patterns a bit. And also, we are thinking about enhancing the performance of ceiling to floor distance analysis by expanding the field of view of the data acquisition system. And also, we are thinking about advancing portability to fully automate the data acquisition process, maybe using mini PC or low lightweighted batteries and so on. So this is the end of my presentation. Thank you for listening.